Welcome to our first session on robotics. Today I'm going to talk about some of the topics that we're going to learn throughout this course and generally what you can expect to learn by the end of the course. Let's first talk about robots. Robots are thought of something futuristic, but the fact is they're very common. For instance, they're used in manufacturing lines, in automation to do assembly or welding an object. And we have drone robots that can automatically fly, or we have legged robots that can go through tortuous path. We have robots that can do surgery. We have humanoid robots that have some human capabilities and are sometimes used to do various tasks such as carrying objects or interacting with humans. It's hard to give a textbook definition of a robot. In my opinion, a robot is something that offers a level of autonomy. It automates a task for us. This is a good definition of robot. A robot is a reprogrammable manipulator that is designed to do one or several tasks, and it automates those tasks for us. And what are those tasks? When do we usually use robots? The ideal task for robots have one or more of these features. A task that is dangerous, for instance, if we want to disable mines in a minefield, or explore a very dangerous area, or clean chemical plants. These are tasks that are dangerous for humans. We rather have robots do them. Another example is tasks that are boring or repetitive. For instance, welding or assembling a PCB board for a computer motherboard. These tasks, human has to repeatedly perform these over and over throughout the day, and humans are susceptible to errors. After a while they might get tired and have errors. That's why we rather have robots do it, and robots can do it more efficiently, faster, and more accurately. Another example are tasks that require high precision or speed beyond human capabilities. For instance, in surgery, where we need to cut the tissue in order of a micron, something that's very hard to do for a human operator. That's where we rather have robots. A robot is usually something that has any of these, at least two of these features. It should have a sensing component, so a robot is able to sense the environment, the objects that are around it. Second, a robot has a decision-making unit. It is somehow intelligent. It can decide to do a specific task, for instance, to pick an object and put it somewhere. Finally, it should be able to act, do something. It should have a physical presence, push an object, pull an object, lift something. Usually if it has two of these, we call it robot. For instance, something doesn't have to be a physical robot. An intelligent program that communicates with human users, for instance, the bots that exist in Twitter or Instagram. Throughout this robotic part of the course, we're going to learn some topics. We're going to start with definition of action and perception. How does a robot act? It is usually equipped with some motors that enable it to move, and it's made of several links that are connected with joints that are actuated by motors. We're going to talk about different methods to actuate a robot, and we're going to talk about sensing. How does a robot sense not just the environment and everything around it, but its own position, for instance? How does a robot can become aware of its own features? Then we're going to get into a bit more mathematical concepts, and this is the part of the course that requires a basic understanding of linear algebra. First step is we want to model a robot, mathematically model it, and know how it behaves. We're going to start with rigid body motion and using reference frames, something that you've heard about in the vision part of the course as well. The problem is, how can you mathematically quantify motion of an object, the robot or piece of the robot, in three-dimensional space? We're going to talk about reference frames and how they can use to do so. After that, we're going to talk about forward kinematics. What do we mean by forward kinematics? It's the interesting problem of finding a robot's end effector position as a function of its joints movements. For instance, this robot is made of several links that are connected by joints. Some can rotate, some do a linear motion. And we call the tools that are at the end of the robot end effector. Assuming the position of the robot end effector in 3D space is given by, let's call it X, Y, and Z. And we know the joints can, for instance, rotate by angle of theta 1, theta 2, theta 3, and displacement of D. Our problem, forward kinematics, is to calculate the position of robot end effector as a function of joint movements. The next topic we're going to talk about is velocity kinematics. Forward kinematics gives us the position as function of motion of the robot joints, but robots are usually don't jump between finite states. If it wants to go from this point to this point, it follows a trajectory throughout time. So knowing the position itself isn't enough. We need to know the velocities as well. The velocity of the robot end effector as a function of the velocity of the robot's joints. This is what we call velocity kinematics, and we're going to talk about a subject called Jacobian, which is very common and very we use it actually a lot in the robotics. And next thing is that we're going to talk about inverse kinematics. We said forward kinematics is finding the position of the X end effector as a function of movements of the robot's joints. The joints can rotate or translate. The inverse kinematic is the exact opposite problem, which is actually more interesting, is to know the joints movements as a function of the robot end effector position and sometimes even orientation. Why is this more useful? Because in reality we want the robot to do a specific task for us. Pick an object and put it somewhere else, for instance. We usually know what the task is. If we have a camera, we can measure the position of the object that we want to pick. We know the position of the object. Therefore, we know where the end effector should be. The value for position of the robot end effectors are commonly known. Then the problem is how to move the robot to go and pick the object. We need the inverse problem. We need to know what the joint angles should be in order to get to the desired position. Finally, in the last couple of sessions, we're going to get into more complex modeling techniques, specifically robot dynamics. So far we talked about position and velocity of the robot joints and end effectors. How about if you want to apply force to an object? This is where you need to consider robot dynamics. The dynamics of the robot includes the forces and torques that are applied by the robot to the object, and the force and torques that the motors that are providing for the robot. And again, we have a forward and inverse dynamic problem. The forward dynamic problem is usually what should be the torque of the motors in order to get a desired force and torque at the end of the robot end effector. This is called forward dynamics. Inverse dynamics is opposite. If we have some force and torques applied at the robot end effector, what should be the torques or forces of the motors? This is what we call the inverse dynamic problem. And finally, we're going to talk about control. If we know how to model a robot, how to relate the forces and velocities of the robot end effector to its joints, how can we ask it to do a specific task? This is that decision-making component that we talked about. A controller basically converts a specific task into forces and torques or movements of the robot joints, meaningful parameters for a robot. And we have two different types of controllers, open loop and closed loop control. Consider this robot in the image. It wants to pick an object from this rail and put it on this rail. Assume we have a sensor that we perfectly know the position of this object and perfectly know where it should be. We have a perfect mathematical model of the robot. Everything is very accurate. Then using, for instance, the inverse kinematic, if we know this position as x, using inverse kinematics we can calculate what should be the joint angles of the robot in order to get there, pick the object and bring it here. This is called an open loop control. We know what should be the task, we know all the parameters of the task position, everything. Just tell the robot to do it using usually inverse kinematic or inverse dynamic. But the fact is, in a realistic world, we don't know everything. There is always sources of disturbance and noise. You have probably known this from the vision part of the course. If we want to measure the position of this block that we need to pick using a camera, processing images has some error. The position that we know is not exactly accurate. So the robot wants to go and pick it, it doesn't exactly get there. It gets to a point that has a difference, let's call it delta x. This is an error, it cannot pick an object. Therefore, open loop controllers usually have errors and don't work very well. That's why we have closed loop control. In a closed loop control, we usually have sensors to estimate the error, and based on this error, correct the motion of the robot and do the task more accurately. For instance, we can measure how far the robot has gone from the object, have an estimation of the error, and tell it to correct itself. This is called a closed loop control. There is usually a feedback in the closed loop controller that tells the robot to correct its motion based on the information that we get from a sensor. So these are some of the topics that we're going to talk about throughout the course. The robotics part of the course is usually not really familiar for you, and it's a bit more, it requires more time. So I would like to ask you to spend time on watching these videos and go through some of the examples that we're going to talk about through these videos, and finally come to the live sessions loaded with questions. Thank you very much.